Hi, this video will be about the Fourier series representation of periodic signals. Now, what do we mean by a periodic signal? We have defined this before. A signal is periodic if the following condition is satisfied. X of t is equal to x of t plus capital T for all t. Capital T is the period of this periodic signal, and as you remember, there may be several periods, but among them the smallest period is the fundamental period, which is denoted by T0. So the fundamental period of our periodic signal. So this is our periodic signal. X of t is periodic with period capital T. And among these possible periods, we have the smallest one, which we name as the fundamental period, denoted by T0. Now we have considered the complex exponential signal x of t e to j omega 0 t as a very important periodic signal in signal theory, where omega 0 is our angular frequency, in this representation of the complex exponential signal, and the fundamental period is just 2 pi over omega 0. 2 pi over omega 0. Now, if you remember our previous discussions related to the complex exponential signal, there we have mentioned that the complex exponential signal is important in signal theory because it is used as a building block. Complex exponential signals are building blocks of signals. Now, what do we mean by this? This means that we will be able to represent signals, arbitrary signals, in terms of a superposition of complex exponential signals. So, how do we do that? Now, first, let us start with a certain definition of a set. Now, consider the set of signals e to j k omega 0 t, where the index k is an integer running from minus infinity to plus infinity. So we have a set of complex exponential signals whose angular frequencies are k omega 0, where k is an integer. So we have complex exponential signals with frequencies equal to integer multiples of omega 0. Now this set is called the set of harmonically related complex exponential signals. Okay, now, for example, let us look at some of these signals in this set. The set obviously contains infinitely many signals, complex exponential signals. For instance, when k is equal to 0, we have the signal e to j 0 omega 0 t, which is equal to cosine 0 omega 0 t plus sine together with the imaginary units j sine 0 omega 0 t. Okay, let me write this below. So this is cosine omega 0 t 0 times omega 0 t plus j sine 0 omega 0 t. Now you see that this is equal to 1, this is equal to 0. So k equal to 0 gives us the signal which is equal to 1. So it is the constant signal whose value is 1 for all t. K equal to plus minus 1 will give us the two signals e to j e to plus minus j omega 0 t. So these two signals are called the fundamental harmonics or first harmonics. For k equal to plus minus 2, we have e to plus minus j 2 omega 0 t. Now these are called the second harmonics, etc. So we have the higher order harmonics as, for example, k plus minus 3 will give us the third harmonics and so on. Now, after looking at this set of harmonically related complex exponential signals, we have a certain claim, and in fact it is the Fourier series representation. And it is the following. Our claim is the following. This is one of the most remarkable results in not only in signal theory but in the history of mathematics. It is one of the most important and remarkable results. Let x of t be a periodic signal. So we have an arbitrary periodic signal with fundamental period capital T0. Then x of t can be represented as x of t is equal to the series k running from minus infinity to plus infinity, ak e to j k omega 0 t, where omega 0 is related to the fundamental period of the signal x of t as follows. Omega 0 is equal to 2 pi over t0, and AKs are, well, they can be real as well, but in general they are complex constants to be determined. Okay. Now this is the so-called Fourier series representation of the periodic signal. Therefore, after defining the set of harmonically related signals e to j k omega 0 t with k running from minus infinity to plus infinity, now we claim that any periodic signal can be represented as a series, which is called the Fourier series, given by the expression k running from minus infinity to plus infinity ak e to jk omega 0 t. Now here, as you see in this series expansion, we have the following operations. In fact, we have the multiplication of each complex exponential signal by a constant, which is a complex constant in general, and then we have addition operations in the series expansion. Okay, so we have addition and scalar multiplication operations. So in other words, we have the well-known superposition action in the representation of signals. So the signal, the periodic signal, can be represented as the superposition of complex exponential signals which are harmonically related. That means their frequencies are integer multiples of a fundamental frequency omega 0, which is related to the original periodic signal, the period of the periodic signal, by means of this expression omega 0 equal to 2 pi over t0. Okay, so the next question to be answered is the following. We claim that we have such a series representation where we have those coefficients, the complex constants in the representation. How do we evaluate those coefficients? So that will be our next question to be answered in the coming video. Okay, so thanks for listening.